Okay, great. Thank you very much. So thanks a lot for the invitation, and thanks to Sergey, who'll probably join in a few minutes as well for the invitation. It's a rare treat to talk to such a distinguished audience. So the stuff I'm going to talk about today is probably a little bit tangential to what most people have been interested in and have sort of been discussing here, but hopefully some of it is still of some interest. And it's really more an operator theory question, but there's some links with harmonic analysis and so on. And everything here is joint work with my colleague, Sasha Pushnitsky at King's. So this is based on a little joint project we did before. Okay, so I'll sort of make a start, and I'm not sure quite what everyone's background is. So some of the stuff will be just a bit of a recap at the beginning. So apologies if it's very basic. But yeah, preferable to be basic than the other way around. So, okay, let me first define Hankel matrices, which is sort of the main things I want to talk about. So you start with a sequence, just any sequence of complex numbers. Then the Hankel matrix, which I'm going to just denote as this H of alpha, where alpha is my sequence, is just a matrix that's just constant on these diagonals. Can I get it? Yeah, so it's just constant on diagonals, okay? So these, come up very naturally in many, many areas. I imagine some people will already be very familiar with them, some people less so. And as usual, we think of this as just an operator on little L2 in the usual way. So there's sort of another way to define these, which is sort of a continuous version. And okay, you want a continuous version of this. So your sequences become functions. Hi, sorry. Your sequences become functions, and your sums become integrals, and the definition sort of writes itself for the integral version. And basically the integral version looks as follows. So you start with, well, okay, more generally, you can just have a distribution, but let's just make it locally integrable for this moment. And yeah, it's defined in exactly the same way. It's an integral operator on L2 of the positive half line, and it's completely analogous to the Hankel matrix. So everything I want to discuss is basically about ways to relate these two objects. And in particular, we're sort of looking for like transference type results from the integral operators to the discrete versions, the matrices, okay? That's the idea. So there's already sort of a very good sort of transference method, which is that these are actually unitarily equivalent, or these two classes are unitarily equivalent. And it's quite explicit. So they're unitarily equivalent by what's called the Laguerre transform. So if you don't know what that is, don't worry. I may mention it once more later, but probably not. We'll see how time goes. And even if I do, it's not important that you know what it is. But basically, if I just expand in the basis of Laguerre functions in L2 of R plus, then my integral operator just has a Hankel matrix. So this gives us a way of kind of transferring results from one to the other. But often we sort of only have, for example, say a rate of decay for our integral kernel or something like this. So we're looking for things that are, one, a little bit more easy to use, and also in some sense, maybe are a little bit more natural. Okay. So I'm also going to be talking a lot about Schatten classes in particular. So just by way of recap, because I'm not sure how familiar everyone else is with these. So I'm just going to recap what these Schatten classes are very quickly. So apologies if this is very, very simple and you know this already. And okay, so by way of recap or by way of introduction, if you've not seen this before, if you have any operator on a Hilbert space, you can define its singular values. So this is just the distance to the rank n operators. Now, of course, if your operator is compact, that means it's approximable by finite rank operators. So these singular values go to 0, right? That's what compact means. So So the Schatten classes are, in a sense, degrees of compactness. These are sort of a quantified compactness. So the Schatten class SP is all operators whose singular values are in little LP. Okay, so in particular, they're compact, and of course, as P goes to 0, they become more compact, right? This is the idea. Okay. Particular special cases are S1, which is what we call the trace class operators, or S2, the Hilbert-Schmidt operators. Okay. So now let me move on to the actual topic that I sort of want to discuss. So here's the kind of motivating example. So I've got a continuous function on the positive half line. So this I can use to form an integral operator, a Hankel operator. So I'm just going to restrict it to integers. So the plus one here is irrelevant. It's just, it might not be continuous at 0. So you're just sampling this at some discrete set, and you're forming the Hankel matrix. So the question is it true that if I start with a bounded operator, then I get a bounded matrix if I just take the integer values? So it's not so difficult to see that the answer is no in generality for this. You could also ask, well, what about Schatten class? If I start with something that's better than being bounded, that it's actually in some Schatten class, then is it true that the matrix I get by doing this sort of restriction is also in the same Schatten class? So is this a bounded map? I'll kind of state this a bit more precisely in a second. It turns out yes for p less than or equal to 1. So only for small p is this true in general. So more generally, I'll look at sort of a slightly more general type of restriction where instead of just sort of brutally restricting at integers, we just take little local averages of our integral operator. So if you think of this as, say, a little bump function or something, and in fact, so if this is, if you sort of formally take this to be a point mass, like phi to be a point mass, then you just recover this pointwise restriction. But you can allow for like little local averages or things like that. And the idea is that the smoother this phi is, the more regular this is, the better estimates you get, the more classes you preserve. This is the idea. Okay. Any questions so far before I carry on? Please feel free to interject at any point. Okay. So there's nothing really, in a sense, this question that I've asked, actually, there's nothing really very Hankel about it at all, because you could take any integral operator, restrict it and make a matrix and ask exactly the same questions, right? So yeah, okay, let's take a general integral operator here with some continuous kernel, say, and I restrict it, and I form a matrix, and I just look at the integer values, and I ask, do I have an estimate of this type? So is it bounded on these Schatten classes? So exactly the same question. And it's really not difficult at all to see that the answer is no in generality. You can't do that for any Schatten classes. And a counterexample is very, very simple. I can kind of tell you in kind of completeness now. So if you just take, for example, that K, this integral kernel K is just a product of, it's like a tensor product of two functions. Then this gives you a rank 1 operator. And so it's rank 1, so its operator norm and all its Schatten norms agree. And in fact, it's just the product of the L2 norms of these two functions. So all the norms are equal. And then it's very, very easy to see that you can just, it's very easy to choose these functions to make the L2 norms go to 0, but to keep the values at integers the same, right? You can't control the L2 norms by the values of the integers. So in general, the answer is certainly no. So you really do need some additional structure for this question to be meaningful. And yeah, for us, that structure will be this Hankel structure. Okay. So yeah, so. Well, the problem is for general L2, yeah. So if you insist that, for example, your kernel is sufficiently smooth, if you put some very strong regularity assumption on the kernel, then you can get somewhere. But in general, so for general sort of, yeah, even continuous kernels, you can't do this. But yeah, you're sort of right in that the smoother it is, the more dense, the sort of less densely you can sample, right? But yeah, you do have to have some kind of smoothness restriction, I think. Did that answer your question?
Yeah.
Sure.
Yeah.
Okay. Okay, so a lot of people, if you've come across Hankel operators before, you'll probably have come across them in the context of, say, Hardy spaces or sort of function theory or something like this. So I'm not really going to pursue that so much in this talk, but just to kind of make the point that any Hankel operator, you can associate what we call a symbol. So in the case of a discrete operator, you just look at this analytic function. In the continuous case, it's just a Fourier transform or the inverse Fourier transform, depending on what you choose to call it. But yeah, you can associate these functions to the operator. So, okay, for sort of full disclosure, there are really many symbols because you can extend this to sort of the negative frequencies however you like, and you still get another symbol. So this really is called the analytic symbol, and this is unique. And a big sort of this whole industry about these operators is essentially the problem of relating the operator theoretic properties of the operator to the function theoretic properties, or analytic properties of this symbol. That's sort of the aim of this entire program, I guess. And so this is already quite a successful program. In particular, this matrix is bounded precisely if this symbol is in BMO, so space of bounded mean oscillation. So maybe I should say, so it was Nahari who sort of proved this because he proved that this matrix is bounded if the symbol can be extended to a bounded function. So in other words, if it's the Riesz projection of a bounded function, and then it wasn't until Pfefferman proved the H1 BMO duality that it was, that we saw that this was just BMO. But I guess this is how we would state it now. Similarly, for compactness, you have a criterion, and it's sort of the same story in that this is really Hartmann, and then Saracen came up with VMO, and we could state it in this way. But yeah, if it's compact, then it's in what's called vanishing mean oscillation. And if it's in this Bessel, if it's in this Schatten class, then the symbol actually has to be in a Bessel space. These Bessel spaces, BP or BPP, I guess. Okay, so we have a sort of a function theoretic criteria for all of these things, and this is quite a productive way to sort of approach all of these problems. So it's worth thinking about what is these restriction maps. What's the induced map on the symbol, right? What happens to the symbol? And so if you do just this, if you restrict by taking an average like this, then the corresponding symbol basically looks like this. So this is a periodic function, right? Z lives on the unit circle. So the way you should really think about this is as follows. So you're multiplying by phi, but because the bottom is periodic, if you sort of cut up the integral onto unit intervals, what you're really doing is sort of periodizing just the top. So you're multiplying by something, which if it's smooth, it will give it some decay. You periodize it, and then this integral is just taking the Riesz projection. So you're just projecting onto the analytic part. That's what you're doing, right? Okay, so this is for point-wise restriction. So if you take phi just to be a point mass, it really is just a periodization, basically. And so these questions are really, well, is this map bounded on BMO, from BMO of the real line to BMO of the unit circle? Or the question about Schatten classes is just whether this map is bounded on the corresponding Bessel spaces, from the Bessel spaces on the real line to Bessel spaces on the unit circle. Okay. So if you're familiar with Fourier multipliers, and if you're not, don't worry, it's not so important, then you'll sort of recognize that this sort of circle of problems has existed for a while in that context. So these results, the stuff I'm going to kind of describe to you sort of parallels these types of results. So just for context, this is, so Fourier multipliers on R are just bounded functions. Yeah. Yes. Yeah. Oh, this is all P for any given P between 0 and infinity. That's right. Yeah, I mean, oh, well, you could define it in tons of ways, but yeah, I think the only way I would be able to write down for you immediately is by the Fourier transform. Yeah. Yeah. So I mean, okay. So this is really, I should be a little bit more careful here. So this space really is the homogeneous Bessel space, BPP 1 over P. So there's a. Yeah, and again, if you're not familiar with these function spaces, don't worry. It's not so important. I'm not actually going to do any sort of calculations or anything. I just want to make the point that really you can sort of think of this as sort of a transference result on sort of various function spaces as well. Or if you're an operator theorist, you would think about it in terms of Schatten classes, but it's completely equivalent. Okay, yeah, so these Fourier multipliers. So yeah, a Fourier multiplier on LP of R is just a function where you take, it's an operator defined as follows. You take Fourier transform, you multiply, you take inverse Fourier transform. So it's just a convolution operator. And you can put a norm on this by giving it the norm of the corresponding operator. And similarly, you can define the same thing on the integers. So these are convolution operators on the unit circle. And people have studied sort of transference results on these for forever. I mean, it goes, I think, back to Calderon. But just a few highlights. This is by no means exhaustive, but just to sort of set the scene a little bit. So yeah, there's a famous result of Deleuze in 1965, which tells you if you just take a Fourier multiplier on LP and I restrict it to integers, okay, and it has to be regulated. Well, so some continuity assumption. I restrict it to integers, I get a Fourier multiplier and I get a norm bound of this type. In fact, the constant is 1. And then later, I think it was Agari who showed that actually if you sample at higher frequencies and take the supremum, then the norms become equivalent, actually. So this is a characterization. And then there was some stuff on sort of the reverse process, so extending a sequence. So I think Jodé looked at, say, taking piecewise constant interpolation or piecewise linear interpolation of a sequence and showed that you also get a norm bound. And then this kind of really took off, and I think Koifman and Weiss really treated this very systematically, and then lots of other people, I think Marcus Hauser I mean, this is sort of taken on a life of its own. And now people look at all sorts of things and non-immutable group actions and non-commutative versions and all sorts. But this is quite classical stuff. Okay. So now let me tell you some actual results. So the first result is sort of not so difficult to prove. So it's basically what I said at the beginning, which is if you have P between 0 and 1, so only for small p, and you know that your Hankel operator, your integral Hankel operator is in SP, and you take this pointwise restriction. So again, the lambda is not so important. You just basically have to move a little bit away from 0. Then actually the matrix is also an SP, and you have an estimate of this type. So I've put this in just to show you the dependence on lambda. So as lambda gets close to 0, you have sort of a 1 over lambda kind of blow up on the constant. But yeah, so this is kind of the first result. And this is really not that difficult to prove. So essentially, there are 3 ingredients here, which is that the norm, you basically work with best of spaces. Use the fact that the Schatten classes are just, you look at the symbols and look at the best of spaces. You then look at the Fourier transform characterization of these, so the Littlewood-Paley characterization, and you apply the Poisson summation formula, and that's basically it. Okay, this is really not I guess, that deep a result, but it's sort of the first step. And so just a couple of comments sort of in order here. This restriction is sort of legal, because if I'm in SP for p less than or equal to 1, then this integral kernel is necessarily continuous. So this is sort of a well-defined operation. This does not hold for any p bigger than 1. So even if you restrict yourself to continuous things to make this legal, then you do not have an estimate like this for any p bigger than 1. You do have sort of a partial converse, which is a bit like the Igari theorem I mentioned, which is, if you sample it, sort of look at sampling its sort of different densities, different frequencies, so multiples of, say, gamma rather than multiples of 1, then actually the Schatten norm of the integral operator is equivalent to this quantity. If you take the supremum, and the supremum will happen as gamma goes to 0, of gamma times these SP norms. So this is like a sort of a partial converse. So one inequality is true for all p, by the way. It's just the reverse one. Okay. So it turns out, okay, so you might think, okay, well, that's it. That's the best you can do with these pointwise restrictions. But actually, if you restrict your class of operators a little bit more, you can do a little bit better. In particular, if you insist that your operator is non-negative in the quadratic form sense, then actually these restrictions make sense a bit more generally. In particular, if it's non-negative, then the integral kernel is continuous and monotone decreasing. And it turns out that in this case, you do get estimates for all p, actually, and for the operator norm. So in this case, it's the same setup as before, but now you get an estimate on the operator norm. So if it's bounded, then the restriction is also bounded. If it's compact, the restriction is also compact. And now this estimate that we had before actually holds for all p. And in fact, the only property really we use is that it's continuous and decreasing, that the kernel is continuous and decreasing, and then it's true. So there's sort of a function theoretic consequence. Again, you can phrase this in sort of function theory terms. So a consequence, for example, is as follows, that if I start with a function of bounded mean oscillation or vanishing mean oscillation, and I know the Fourier transform is continuous and monotonic away from 0, and I periodize it, so I just restrict the Fourier transform to integers, then the new function is still in BMO, and I have a norm bound. I don't know, perhaps there's many harmonic analysts in the room. Maybe someone will tell me that this is sort of clear for some other reason. That'd be nice to know. But yeah, this wasn't clear to me at least before. So if I just go back to this, actually, we have sort of 2 arguments for this. So one argument is very much, I guess, yeah, harmonic analysis, square functions type argument, and it's a little bit involved. But nonetheless, so that's kind of one way of doing this, and that's we have another argument, which is purely operator theoretic and very short, that I can give it to you in its entirety in one or maybe two slides in a second. And it's really simple. But it only works for P and even integer and for the operator norm. This is the, I guess, the drawback. So because that argument is so short, I will describe it to you. So I said it's short, but where you use sort of some heavy machinery, which is you use sort of a deep theorem of Barry-Simon, which tells you that if I've got two integral operators on some L2 space, right? And I know that the integral kernel, or say K1, the one integral kernel, is dominated pointwise at each point by the other integral kernel. So in the, I guess, terminology of people who do this, spectral theorists and so on, they say that one operator is pointwise dominated by the other. Then, in fact, you have that the norm of K1 is dominated by the norm of K2, and all Schatten norms are dominated where P is an even integer only. And this is known to be false when P is not an even integer. And this is why, P an even integer in this result is sharp. So this argument that I'm going to give you does not extend to other values of P. And also the compactness of one implies the compactness of the other. Okay, so this is really where all the work is in this theorem, in this argument. So for simplicity, assume lambda is bigger than 2. For lambda smaller than 2, you have to do some other stuff, but it's not such a big deal. Okay, so if lambda is bigger than 2, then you just define, you had your integral, your function a, this bold-faced a, and you just define your integral kernel as follows. You look at a of lambda plus the integer part of t plus the integer part of s. So it's sort of constant on squares. If you're thinking about it as a function on the, say, a quarter plane, it's constant on squares. Okay. But lambda is bigger than 2, and a is monotonic. So if lambda is bigger than 2, you get that this lambda plus the integer part of t plus the integer part of s is bigger than t plus s, which tells you that this is bigger than a of t plus s, because a is, by assumption, monotone decreasing. So in other words, your new integral operator pointwise dominates your Hankel operator. And so the Barry-Simon theorem gives you this immediately. So now all you have to do is relate K to your Hankel matrix. And okay, so if you just check what the quadratic form for K is, if you just test it on some function f, the fact that this is constant on squares means you can cut up your integrals and pull it out. And so you're left with a quantity that looks like this. And here you're just averaging f over intervals. That's all you're doing. Okay. So in other words, you've basically written K as a tensor product here. You're decomposing L2, your big L2, as little L2 of Z, tensor L2 of the interval. And you've got this as a tensor product with a rank 1 operator. And this rank 1 operator is just a projection onto the constants, okay, on each interval. So K and this Hankel matrix have the same norm and same Schatten norms, which gives you the result. And in fact, if I just go back, notice it gives you that the constant is 1. So it's actually, it gives you a better thing than the other argument for lambda bigger than 2. So it gives you that you have a constant of 1. Okay. Right. Right, so the other kind of restriction theorems we looked at is as follows. So take a continuous function now. And if you basically, this restriction, you just average against this phi. So you're basically convolving against this function and then taking the samples. So here we were interested in kind of trying to preserve these SP estimates for all P, right? And seeing the question is basically, what regularity do you need on phi in order to have estimates for all P? So delta functions don't work higher than P bigger than 1. So the question is, if you want to preserve all P, then what do you need? And we have the following results. So the following are equivalent. So the first is, if I periodize phi hat, then this actually has to be bounded. This has to be a bounded function. So notice this is a smoothness assumption, right, on phi. So if this is true, then necessarily you have that this restriction map is bounded in the operator norm and in all SP norms. And this map has norm at most A. So the norm is precisely this, or at most that, sorry. And in fact, it turns out that if that's the case, then something much stronger is true. That actually you have two bounded operators such that this matrix is just your original operator is conjugated with these two bounded operators. So it's clear that this implies that this is really a much stronger thing. So this is sort of useful also because maybe I should say one of the motivations for this was that we wanted to sort of get some results on spectral asymptotics for various Hankel matrices, and this allows you to do this, even if whereas just a norm bound isn't strong enough. Okay. So we looked at sort of one a bit more general framework, which I won't really spend too much time on. So you could also look at a slightly more general Z action than just a shift, right? So you could take, for example, a finite measure and do the following and just say, well, okay, if I define phi j to be phi convolved with this j times, and then I just average against this, right? So this gives you a group action. And by the way, so notice that if I just take a point mass, then this just recovers what I had before. So this is a slight generalization. And in this case, we have the following result. So this is not, I wouldn't say a complete result, but nonetheless. So if you know that your measure has the H infinity norm is bounded by 1, so this basically controls the growth. And you know that phi hat decays sort of quadratically. So again, this is a smoothness assumption on phi, right? So if you, then you're back in the situation you had before, which is that actually H of alpha is just your integral Hankel operator conjugated by two bounded operators. And so necessarily then it preserves this restriction map, preserves the operator norm, it preserves compactness, and it preserves all Schatten classes as well. So the reason I mentioned this is because at the beginning I said that you have that these Hankel matrices and integral Hankel operators are unitarily equivalent by the Laguerre transform. So this is sort of like one end of the scale. On one end, you have these pointwise restrictions, these very naive way of kind of going from one to the other, which really doesn't preserve very much. And on the other end, you have this sort of unitary equivalence. And we sort of wanted to understand how kind of the scale in between, right? How this sort of fits into this slightly more general framework. So in this case, basically you do the following. So if you choose your phi appropriately, if you choose phi to be just this exponential function, and you choose your measure appropriately, which is just this, then okay, these satisfy the conditions of the theorem. So you can, this decays quadratically and this is bounded. So yeah, you can apply the previous theorem. And so one thing I should have mentioned is the last theorem actually the proof gives you the operators phi1 and phi2. So you can write down what these are. And so in this case, your phi1 and phi2 are precisely this Laguerre transform that we had at the beginning. Again, don't worry if you don't know what it is. I wouldn't be able to write it down for you if you asked me anyway. And so this choice recovers this unitary equivalence. So this is just a way of fitting in that unitary equivalence in this slightly more general framework. So that's sort of why we were interested in that, just so that we can try to understand this. Okay. So in the last few minutes, I just want to discuss sort of a converse operation, which is what if you start with a sequence and you want to construct an integral operator? Then what can you do? So, okay, so let's take a function or some distribution on R plus, and I'm just going to interpolate by this function. So I'm just going to construct my function a of t by taking my sequence and just sort of interpolating by phi. So again, you could ask exactly the same questions with this. So it's worth noting that this is just a point. So the boundedness of this map in SP or in the operator norm or whatever is really just the boundedness of a pointwise multiply, right, on the corresponding symbol space. So all you're doing is you're extending by periodicity of multiplying. So this is a pointwise multiplier assertion. But again, there are sort of several ways to prove some of these results. One is operator theoretic. We have some operator theoretic arguments for some of them and some purely function theoretic arguments for some of them, which I think is quite nice. Okay, so the sort of most naive thing you could do is just take a point mass. You just attach a point mass at each integer and see what happens. So in this case, boundedness is straightforward, but you don't end up in any SP class. You're definitely not regular enough to be in any sort of SP class. Okay. So maybe it's worth just mentioning. So with the restrictions, it's sort of easy to preserve small low p, and it's much harder to be bounded in the operator norm. Whereas in this case, it's the opposite. You basically use whatever function you like, and it will be bounded in the operator norm. But because it's much higher regularity, low p is higher regularity, right? So it's yeah, it's sort of much harder to map into this class. Okay. So in this case, we have sort of a following result. We've got a few other results as well, but this is sort of like I guess the most direct thing. So you want to preserve all p. So here we're just thinking of p bigger than 1. Okay, so let's just take p bigger than 1. So we're in the Banach space setting. And then in this case, okay, so if I start with a sequence and my sequence is just 1, 0, 0, 0, 0, 0, so on. So it's just 1 point. And I apply this extension, then what do I get? I just get phi back. So if I want to end up in SP, then the integral operator h of phi has to be if I want to end up in SP for all p bigger than 1, in other words, I want to end up in S1, then this has to be in S1. Similarly, if my sequence is 0, 1, 0, 0, 0, 0, I just get that same function shifted by 1. And this has to be in SP. This is sort of clear. And in fact, you can do this for any k, but it turns out that just these two is enough. So if you know that these two are in SP, then in fact, you get that if you start with something in SP, a sequence in SP, and you extend it using phi, then actually you end up with an integral operator in SP. And you have this norm bound. So this is actually, maybe it's worth mentioning, this is equivalent to saying that phi is in the homogeneous Besseff space B11. So this restriction, basically the fact that this one is also in S1 is like a restriction on the behavior near zero. So that tells you that it's actually in the homogeneous Besseff space as opposed to the inhomogeneous. And then it follows that all shifts are also in S1. Okay. And if you also have that if your operator, you start with a bounded matrix or a compact, then you get something bounded. And so this is, we have sort of, again, a couple of arguments, but basically this is sort of, you just look at BMO. So this one is not so difficult to prove because you use the fact that BMO is conformally invariant. And so the pointwise multipliers are conformally invariant. And so, yeah, so being in S1, so B11 is sort of the smallest conformally invariant space you can have, in the sense that it embeds into all other conformally invariant spaces. And then this one is a little bit harder to prove, but nonetheless, it's sort of you just do use the little Paley theory, and then in real interpolation does the rest. So actually, in fact, you really get this for not just Schatten classes, but what's called Schatten-Lorentz classes. And these are things whose singular values are in a Lorentz space. So this is, you also get this by real interpolation. Okay. So a consequence of this is that if you take phi to be a tent function, it tells you that, say, just piecewise linear, you just join the dots, and this gives you something that preserves all SP classes. So not through this theorem, but if you work a little bit harder, you can also see that, say, piecewise constant interpolation is bounded in SP, but not bounded in the operator norm. So it's not a consequence really of this theorem, but of a sort of related result. So it's not bounded in the operator norm. Okay, so perfect. So I think I'll stop there. Thank you.
Thank you very much.
Thanks.
Other questions, comments? Your restriction is not bounded, as you told us, from SP to equal SP. In the beginning.
Yeah, okay.
But maybe bounded to wider class, so not from SP to
So like
minus 5.
Yeah, I see what you mean. So maybe it's bounded from like SP to a larger P or something.
Yeah.
SP to SQ, where Q is bigger than P or something like this. Yeah, so that's a good point. Yeah, quite possibly. I don't. That's a nice thing to think about. I'm not actually sure. I haven't actually thought about this, and wouldn't be able to tell you immediately. Yes, yeah. I've spent many hours with this on my desk. Yeah, probably more so than any other book. So, yeah.
A sequence A, G plus lambda positive.
Yeah.
And the constant of the operator goes up as lambda goes to 0.
Yeah, that's right. Yeah.
My question is, could you apply extrapolation here to go to lambda 0 and then to consider a log perturbation of this operator and achieve the end?
Sorry, I'll be honest. I don't quite understand. Sorry. Yeah. So let's say this one. Yeah.
So
Okay.
if lambda is equal to 0, right? Because then the norm goes up.
Mm-hmm.
But now my question is, could you apply here extrapolation theory?
Okay.
You have a sub-control of the constant as lambda goes to 0, such that you can get still boundaries But then the point that you have to modify the multiplier instead of taking A of J plus lambda, take A of J with some logarithmic perturbation. I don't know, A of J times log J, something like that.
Yeah.
Does that this limiting operator is bounded from SP into SP?
Quite possibly. I'll be honest, I'm not really an expert in sort of extrapolation theory. Yeah, I think I'd have to think about that more carefully, but that's a great idea. Yeah, sorry, I don't actually know. Yeah. Okay. Ah, this is why I like coming to things like this. Yeah. Okay. Thanks a lot. Okay. Thank you.